Hello and welcome to this video on intermolecular forces. It has specification reference 3.1.3.4 and 3.1.3.7. Here's what we're going to learn in this intermolecular forces video. We're going to look at simple molecules as opposed to macromolecules or ionic structures or indeed metallic structures. And we're going to look at the bonding and the forces that occur between those molecules, not within those molecules. That would be intramolecular forces. So between the molecules there are three types of intermolecular forces. And then we want to see how those intermolecular forces determine the melting and boiling points of various simple molecules. And in certain circumstances we see that simple molecules can form crystal lattice structures, i.e. regular structures of repeating units with the simple molecules as solids. So firstly, let's just name these three intermolecular forces that act between the molecules. Again, not within the molecules, that would be covalent bonds. But between the simple molecules, what are the three types of intermolecular forces? Well, the first one is called induced dipole-dipole, and just to explain this, induced means it's temporary and it doesn't last in time. It just in fact lasts for a moment in time. And dipole-dipole means that a dipole is just where you've got a slight positive charge and a slight negative charge at either end of a molecule, and we would have an attraction between that and another dipole in another molecule. And if they are temporary, that's called an induced dipole, and this is also known as van der Waals forces. Van der Waals forces. So that's the first one, and they are in fact the weakest of the three intermolecular forces. The second one are permanent dipole-dipoles. So again, we've got a dipole and a dipole, so that would be some sort of dipole that exists in a molecule, and a force of attraction that would exist with another dipole that exists in a different molecule, but in this case our dipoles are permanent, and so the intermolecular forces can be permanent, and they are slightly stronger than the induced dipole-dipoles. And lastly, we have hydrogen bonds that only exist in certain molecules, and they exist because of the larger difference in electronegativity between either oxygen, usually, and hydrogen, as in water, or fluorine and hydrogen, as in hydrogen fluoride, and a couple other cases that we'll come across. And these, of the three intermolecular forces, these are the strongest. But they're still only about a tenth as strong as a covalent bond. So there are the three different types. Let's investigate them one by one, starting off with induced dipole-dipole, or indeed van der Waals forces. So van der Waals forces exist in all simple molecules, but indeed if there are other intermolecular forces, especially hydrogen bonds, but also permanent dipoles, then they would swamp the weaker van der Waals forces, and they cause all atoms and molecules to be attracted to each other, even the noble gases. Let's have a look at this in principle. So let's say we've got a bunch of molecules, and I'm going to draw a molecule here with a charge cloud, and let's say this is close by to another molecule whose charge cloud I'll draw like that, who's next to another molecule whose charge cloud is like that, and let's have one last molecule there whose negative electron charge cloud are all drawn in those green shaded patches like that. Okay, so the thing about electrons is that they don't stay in one place. They zip around all over the place, and so in any particular moment in time, this particular area might contain instantaneously more negative charge than the other area, just because of random movements of electrons. In which case, this area would be negative, and if that area is negative, then this area would be positive. And so that random movement of electrons has created a dipole that only exists for an instant in time. But what it does is it affects the adjacent molecules. So for example, this positive charge here would attract the negative charge of the adjacent molecule. All right, so it would the electron cloud would rush over there, and then this area of this molecule would become positive, leaving this negative temporarily. And then you can see a chain reaction happening here, can't you? So this negative charge here would affect an adjacent molecule, so that the negative charge would rush away from that, would be repelled away from that, leaving this part of the molecule as positive and this part of the molecule as negative. And you can see the chain reaction that would happen there. And when that does happen, then there's a little force, electrostatic force of attraction between all of these opposite charges, and that is the van der Waals force. So let's draw a little line out here. So this is the van der Waals, or the induced dipole, is the electrostatic attraction between these temporary dipoles, or these induced dipoles. And they're quite weak, but they exist in all atoms, so that even the noble gases can have these van der Waals forces. So you can actually freeze and solidify the noble gases, because there exists van der Waals forces between those atoms. And if you remove enough energy from a sample of simple molecules, then the van der Waals forces can still make the molecule solidify into a crystal structure, which would be called a molecular lattice, and that's what we're going to have a look at next. And we'll illustrate that point, the point that van der Waals forces are responsible for holding, for example, iodine molecules together in a lattice. We'll look at the iodine molecule, which you will remember is I2. So we've got an iodine atom covalently bonded to another iodine atom in I2. And you know at room temperature that it is a solid. And if you've seen it as a solid, it looks a grey crystalline structure. And so the reason why it's a grey crystalline structure is because of these van der Waals forces. So let's draw a little positive nucleus of an iodine atom and another little positive nucleus of an iodine atom. And we're going to have a charge cloud around that. And we're going to have a charge cloud around the other atom in the molecule. And let's say we have a temporary dipole. You might get, for example, this one being slightly negative at this edge of the molecule, and this then would be slightly positive. So an adjacent molecule, which might be here and here, with its charge cloud like this. If this end here is slightly positive, that's going to induce a slightly negative charge in this molecule, that end of this molecule, which leaves this side of the molecule as slightly positive. And we can repeat this, which I'll do a few more times. So let's say we have another molecule down here with its charged clouds. So again, this side of the molecule was delta negative, and so this area of the molecule might be delta positive, which would make this one delta negative. And so you can see there's an electrostatic attraction here between the negative one and the positive one, and also between this positive and this negative one. And then we might see this all happening again here. And if this one here is positive, then this one here is going to be negative. So you're going to get another little electrostatic attraction here. And then this one was negative, this one here, so you get another little electrostatic attraction here. And you can see that this is going to build up to be a regular structure. And because my drawing is less tidy, what I'm going to do is I'm going to show you a little picture of what a more realistic picture of an iodine solid lattice. And here it is here. And as you can see, the iodine molecules are arranged in a regular pattern, i.e. a lattice, when it's a solid. And you can see the delta positive here and the delta minus here, so the electrostatic attraction would be here and here and here, and also between this negative end and that positive end, and this negative end and that positive end, etc. You can see how these bonds are going to keep that structure together, like that. So now we're going to move on to consider stronger and less strong van der Waals forces, and what makes van der Waals forces slightly stronger in some molecules and weaker in other molecules. And the point is that larger molecules can have larger electron clouds, meaning stronger van der Waals forces. Let's just draw that. Draw a picture. Let's say you've got a large charged cloud. You can see that there's a greater potential for a difference in charge between each end of the molecule if it's large, compared to if it was just a small molecule. Then the potential for difference between the charges would be much smaller, like that. And so if this is a larger difference in charge, if it's a bigger dipole, then the forces between these large charge clouds are going to be stronger, and in fact that's what results in higher melting points. So this point can be illustrated by looking at the boiling points of the noble gases. Now you'll know that the noble gases are just single atoms, and so they can't have any permanent dipoles there. So the only forces that can exist are intermolecular van der Waals forces. And we're making a point that larger electron clouds have stronger van der Waals forces. And if that were true, then we would see that a larger atom, such as xenon, would have stronger van der Waals, hence higher boiling points, than a much smaller charged cloud, such as happens with helium. And that is what we see when we look at the graph. So this trend of increasing boiling points of the noble gases is evidence for van der Waals forces. and also supports the hypothesis that van der Waals forces are stronger in larger atoms and molecules. But size is not the only thing that affects the strength of van der Waals forces. Shape does as well. Yes, the shape of the molecule also influences the strength of the van der Waals forces. And the point is that if you have a long, straight molecule, it can get quite close to its other long, straight molecules. And so anything that is very close to each other is going to have a strong attraction to each other, stronger than if they were further apart. So those van der Waals forces are evidently going to be stronger when the molecules are closer together, and also stronger when there's a large surface that's available to attract each other. So the large surface and the closeness of the molecules mean that the van der Waals forces in long, straight molecules would be stronger than in molecules of other shapes. So let's look for some evidence for that, and here we have a chart of alkanes of increasing length. So we start off with 1 carbon atom in methane through to 6 carbon atoms in hexane, and as you can see from their boiling points, the boiling points generally increase. And the point is that if the boiling points increase, that must mean it takes more energy to separate the molecules, and that is because the force of attraction between those molecules must be higher. So we can say that the van der Waals forces, which is the forces between the molecules, so the van der Waals is also stronger. So that's enough on temporary dipoles, or van der Waals. Let's have a look at permanent dipole forces now. And here we're saying that the molecules that have permanent dipoles, not the induced dipoles of van der Waals forces, but those that have permanent dipoles, they'll be held together by this electrostatic attraction between the permanent delta positives and the permanent delta negatives. So let's have a look at an example. Let's make that example hydrogen chloride again. So hydrogen chloride, HCl, as you'll remember. So we've got one covalent bond between a hydrogen atom and a chlorine atom. Let's draw them down here a little bit larger. So there we have a hydrogen chloride molecule, and because chlorine is more electronegative than hydrogen, as we've seen before, the bonding electrons, which we'll draw, say, as a blue circle and a red cross, they are drawn towards the more electronegative atom, which is chlorine. And so if those negative electrons are nearer to the chlorine, then that of course means that the chlorine is going to be slightly negative. And if by the same token they are not anywhere near the hydrogen, that's going to leave the nucleus of the hydrogen atom exposed, and so that side of the molecule will be slightly positive. And so when it interacts with other hydrogen chloride molecules, they're going to naturally arrange themselves such that the molecule are going to arrange themselves like this, where you've got the slightly positive hydrogens nearer to the slightly negative chlorines of the other atom, and that goes on and on. So we'll draw that again like this, with our slightly positive hydrogen bits and our slightly negative chloride atoms. And so our forces of attraction, let's switch that to red, our forces of attraction are going to exist between these oppositely charged permanent dipoles. They're quite weak compared to other strengths of bonds, but indeed they would be stronger than temporary dipoles. So these forces here, the red hatched lines, these forces are called permanent dipole-dipole forces. And the last thing we need to do with permanent dipole-dipole forces is to look for some evidence of their existence. And that's what we'll do next. And we'll do that by asking ourselves this question: how could we test whether a liquid is polar or not? Polar being another word for a molecule that has permanent dipoles. Well, we could do the demonstration that you may well have seen, which is when you get a charged rod and you bend a stream of water. And you could do that using a burette, and you could have some water in this burette, and the water could flow out vertically downwards, of course, into the sink, and that would normally happen. And when you would introduce a charged rod to it, so let's draw this charged rod here. Let's say we had a charged rod and we brought it close to the stream of water. What you would see then is you would see the charged rod becoming attracted to the water being attracted to the charged rod and becoming deflected in its path. And if we have a look at this, what's going on here in a little bit more detail, so we'll just show what's happening at the molecular level here. When we've got our stream of water, so we've got a stream of water which is being deflected, and we've got our charged rod here. Let's say we're making our charged rod negative, so we've got lots of extra negative electrons on this charged rod. Then our water molecules are going to arrange themselves such that the delta positive hydrogens are going to be closer to the negative charged rods, and the oxygens, which are delta negative, are going to be further away. And we'll just draw another hydrogen, another water molecule here, where the hydrogens are delta positive and the oxygen is delta negative. So you can see that the water molecules can arrange themselves like that, such that there is then a force of attraction between the delta positive hydrogens and the negative electrons in the rod, and that's going to that force of attraction is going to draw the water towards the rod, and hence cause that change in direction. And so that's how it happens, and that is evidence for polar molecules. But in order to do a control test, what we would have to do is we'd have to do another test, let's say with a non-polar liquid. So let's say instead of, in this one we had water, in this one we might have something that we don't think is polar, which would be hexane. And so let's draw our hexane in purple instead. And so we let the hexane come out the bottom of the burette, and it travels directly down, and then we bring our charged rod to the hexane, and it's got all its little extra negative electrons that we've put onto the charged rod, perhaps by rubbing a certain type of cloth near it. And does it change direction or not? Well, when we do this, we find that non-polar liquids like hexane do not become deflected by the charged rod, and that's evidence for the fact that they are not polar molecules. Hexane molecules are not polar molecules. Yeah, so that's enough on permanent dipole-dipole forces. We'll move on to hydrogen bonding next, which is a particular type of permanent dipole-dipole molecular attraction. And as we've said before, hydrogen bonding is the strongest intermolecular force, but it only happens within certain types of molecule, and that's when hydrogen is bonded to the three most electronegative elements, or three very electronegative elements, as in fluorine, nitrogen and oxygen. So when we get compounds that have hydrogen and fluorine, hydrogen and nitrogen, and hydrogen and oxygen, we could have hydrogen bonding. Let's illustrate hydrogen bonding with a diagram as usual. So we're going to use the example of water. We know that hydrogen bonding exists in water, giving its quite unusual properties. So a water molecule is going to be one oxygen and two hydrogens like that. And what we know is that oxygen is very electronegative, and so it's going to draw the bonding electrons towards itself, and so therefore become negative itself, leaving the hydrogen atoms as slightly positive. But the other thing about the water molecule is that it has these two lone pairs of electrons as well, doesn't it? And so what that means is that the hydrogen atom, the delta positive hydrogen atoms, which are really small, and so this delta positive, even though it's only a slight positive charge, because it's so small, the charge density is very high. It's a high charge density because it's so small. And so that forms a little bond between itself and the lone pair of another oxygen atom. So we might draw that such as this, in this way. So you might have another water molecule here like this, and the lone pairs would be placed here and here with our delta negative oxygen atom and our delta positive hydrogens, and so our electrostatic force would act between our very high charge density delta positive hydrogen atom and one of the lone pairs on an oxygen atom of a different water molecule. And that might happen again. We'll do that one more time to illustrate it. So we've got another water molecule that might be, positioned like so. And in the same way, we're going to have this hydrogen atom is going to be delta positive, as with the other one. The oxygen is going to be delta negative. And we've got a electrostatic attraction between this lone pair and this hydrogen atom of the other water molecule. And just to reiterate, the hydrogen bonding, right, is so strong, right, as in compared to other intermolecular forces, if of course not strong compared to a covalent bond, but hydrogen bonding is so much stronger than the other types of intermolecular forces for two reasons. One is because the bond is so polarized. So in this case, it's the oxygen hydrogen bond. The bond is so polarized, and it's so polarized because oxygen is so electronegative. But it's also strong because the hydrogen, delta positive hydrogen, let's just put a little delta pos in there, our delta positive hydrogen, right, is so small. And because it's small, that little positive is very densely located. And quickly we might do another example. Let's do ammonia. That's another example of a compound that has hydrogen bonding. Ammonia, you'll remember, is NH3, and we've got the molecule sort of shaped like this. And nitrogen, not quite as electronegative as oxygen, but quite electronegative nevertheless. It's going to draw those bonding electrons to itself and therefore become delta negative, leaving the hydrogens delta positive. Yeah, and the other thing about about nitrogen is, of course, it does have, as well as those bonding pairs, it does have a lone pair of electrons as well. And so in the same way as these hydrogen atoms that are delta positive made a bond with the lone pair of an oxygen atom in water, they make a bond with a lone pair of nitrogen in a ammonia molecule. Like that. So hopefully that's clear about hydrogen bonding, and what we're going to go on to do now is to look at the effect that these strong hydrogen bonds have on the properties of the compounds that have hydrogen bonding. Yes, like we said, the hydrogen bonding has a huge effect on the properties of substances, and the sort of property that we're going to have a look at first is boiling points. And if hydrogen bonding is as strong as I'm making out, then what you would expect is you would expect boiling points to be quite high of substances that have hydrogen bonding. And so what you could do is you could look at the boiling points of, for example, hydrogen of hydrides of group 6. So if you looked at the hydrides of the group 6 elements, so group 6 of course is oxygen, sulfur, selenium and tellurium. So our hydrides would be H2O, water, H2S and H2Se and H2Te. So there are hydrides of our group 6 elements, and if we plotted boiling points of those compounds, they would range from about 400 Kelvin to about, so let's say we'll put about 200 down here, so that's 300 in the middle, and water of course 393, so we put water up the top, and then it comes right down to H2S, so this would be H2O, H2S, and then slightly higher would be H2Se, and slightly higher still would be H2Te. And if we try and explain this, why should the hydride of oxygen be so much higher boiling point than the boiling points of all the other hydrides of group 6 elements? Well, that's because of the hydrogen bonding which only exists in water because its oxygen is so electronegative. Sulfur, selenium and tellurium are less electronegative, and so you won't get the same bond polarization. So you won't have hydrogen bonding there. And this upward trend here is simply explained by the increase in size. So the increase in size leads to an increase in van der Waals forces, and that explains that gradual increase in boiling point of those hydrides there. So as well as having an effect on boiling points, it has effect on other properties as well, such as forming regular lattice structures or crystals. And that's what we're going to look at now. And what we're saying is that as liquid water cools to form ice, the molecules, the water molecules, arrange themselves into a lattice structure, and we know that, don't we, from the shape of an ice crystal that we'd probably be familiar with. And when water freezes, then something like this is going to happen. You're going to get a water molecule starting off here, and that's going to bond to another water molecule. Right, so this is going to be delta plus, delta plus, delta minus, delta minus, and you can have this lone pair here, another lone pair, and a hydrogen bond between the hydrogen and the lone pair, and another hydrogen bond between the next delta positive hydrogen. That's going to make another bond. Here, what I'm trying to do is trying to show you how you might get a hexagonal lattice structure. So if you bear with me. There's our lone pair there. We have delta positive. This one's delta positive. And you can sort of see that this is a quite poorly drawn hexagon sort of shape. But what I've attempted to illustrate there for you is that when water freezes to form ice, then the water molecules arrange themselves because of the hydrogen bonds into a lattice structure there that forms a crystalline shape. And it's all held together because of the hydrogen bonds. And it might be worth looking at that in another way as well, with real pictures that you might see in a book, which I've got here for you. So this might be a bunch of water molecules in liquid format. You can see an oxygen atom there, various hydrogen atoms all bonded together. These would be you can sort of see them all squished in together, very densely packed together, with the hydrogen bonds being formed temporarily, and then the water molecules move on and form another hydrogen bond with another water molecule until they freeze. And when they freeze, the hydrogen bonds fix the water molecules in position such that they look like this in a regular crystal lattice, which might to the human eye might look like a snowflake. Okay, and there's a couple of takeaways from this, and that is that the length of the hydrogen bond, right, is a lot greater than the length of a covalent bond. So what that means is that when we get ice, then the water molecules are actually further apart than in water, because the hydrogen bonds basically they're a longer length and they keep the water molecules further apart from each other. So that means that ice is actually less dense. Ice is actually less dense than cold water. I think the water at 4 degrees is the most dense temperature of water, which is not really what you'd expect. Most substances, when they freeze, they become more dense because the solid particles are usually packed closer together. But in fact, not with water, because of the hydrogen bonds being longer than your covalent bonds. Okay, so that concludes hydrogen bonding for now, and you might reflect that we've now done all 3 of the intermolecular forces. So what we're going to move on to now is just to have a look at the behavior of some simple covalent molecules and how those properties or behaviors are determined by the bonding that's within the molecules. So in writing, that's what I've just said. The physical properties of simple covalent compounds are determined by the bonding in the compound, and the physical properties that we're interested in is conductivity, and that would be electrical conductivity really, and also the melting point and the solubility. And what we can say about electrical conductivity is that simple covalent molecules don't conduct electricity. For electricity to be conducted, you need charged particles, electrons, either delocalized electrons as with metals, or electrons that are in abundance on anions as in ions. But in simple molecules we have no charged particles, and so we can't carry any charge, so there's no conductivity with simple covalent compounds. As far as melting points are concerned, simple covalent compounds generally have low melting points because these forces between the molecules, not within the molecules, between the molecules, are weak, and that's whether they are temporary dipole-dipole forces, permanent dipole-dipole forces, or indeed hydrogen bonds. They're all relatively weak compared to covalent and ionic and metallic bonds, and so we say they have low melting points. Even if those compounds with hydrogen bonds have slightly higher melting points than other simple molecules, they're still low compared to ionic compounds, covalent compounds, and metallic compounds. And lastly, solubility. Then simple covalent compounds, some of them dissolve in water, but that depends on how polarized they are. So if they are slightly polar themselves, then they will dissolve in water, because water is polar. But if they are non-polar, then they generally don't dissolve in solvents that are polar, like water. And that's a brief look at the physical properties of simple molecules. What we're going to do lastly is just look at the trends in melting and boiling points, and what determines those trends, what 2 factors determine the trends. And the 2 factors that determine the trends in melting and boiling points are polarity and the size of the molecules. And we're going to do this by looking at some examples and draw a graph of those examples. And the examples we're going to use are the group 7 hydrides. So we're going to say the group 7 hydrides. We looked at the group 6 hydrides before, and now we're going to look at the group 7 hydrides. So that would be hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. And when we look at the boiling points, so let's plot them, boiling points against the hydrides, and so the boiling points of hydrogen fluoride is going to be about it's going to be less than 300, and we need to scale down here to about 150. So this is boiling point in Kelvin. And so when we plot hydrogen fluoride, that's going to be up here, and we go right down to about 180 for hydrogen chloride, and slightly more for hydrogen bromide, and slightly more again for hydrogen iodide. So let's just label those. That's hydrogen fluoride, that's hydrogen chloride, hydrogen bromide, and hydrogen iodide. And if we just joined up those, we'd get a graph that looks like that. So what we can see is, again, hydrogen fluoride, very much higher boiling point than the others, and that is higher like that because of the hydrogen bonds. And the polarity of that hydrogen fluorine bond within the molecule. And you also get this slightly increasing trend because we've got not so much polarity, less polarity in these bonds than the hydrogen fluoride. All right, but you've got a larger size of molecules. So the larger size means the van der Waals is going to increase, so that explains. So the van der Waals is going to increase, and that explains the increase in boiling point between hydrogen chloride and hydrogen iodide. But the very high relative boiling point of hydrogen fluoride is explained by the fact that you've got hydrogen bonds, a very polarized bond with the hydrogen fluoride, and also a lone pair on the fluorine for the hydrogen, delta positive hydrogen, to form a bond with. And that's it for this video lesson on intermolecular forces. But as usual, let's just check we've covered off everything we wanted to. So with simple molecules, we went over the three types of intermolecular forces, those being the van der Waals or induced dipole intermolecular forces. That was number one. Number two was the permanent dipole. And number three was the hydrogen bonds. So that was the first one. Let's give ourselves a tick for that. And then we looked at the melting and boiling points of various compounds and related those to what intermolecular force was involved. And we've also looked at two molecular lattice structures. We saw a diagram of iodine as a solid, and we also saw ice as well. And we saw that they were regular structures, also called lattice structures, and sometimes called molecular crystals. So there we are. We've done our three learning objectives. I hope that's been clear. Thanks very much.